Hey Emma,
What's up, Oliver?
something curious happened and I want you to listen.
Oh, what happened?
It's been getting warmer lately, so I wanted to drink some cold water. I put some tap water in a glass and added ice to cool it down. I put too much water in the glass, and by the time I finished adding ice, it was almost overflowing. Then I forgot I had put iced water in the glass and left it for about 2 hours. But when I remembered and hurried back, all that was in the glass was full of water. I thought the water had overflowed from the glass because the ice had melted. For some reason, it didn't spill at all. I'm absolutely puzzled as to why it didn't spill.
That's an interesting question, Noah. So, you thought that when the ice sticking out of the cup melts, that amount of water would spill, right? That question can be answered by understanding the phenomenon that when water freezes, its volume increases and its density decreases. If you understand the principle of buoyancy, I think you'll be convinced.
I've heard a bit about ice being lighter than water, but I don't really understand it. Can you explain it to me?
Of course. So this time, I'll explain why the density decreases when water freezes and the principle of buoyancy. First, let's explain why the density decreases when water freezes. Mia, do you understand the relationship between the densities of a typical solid, liquid, and gas?
If I remember correctly, a larger density means it's heavier for the same volume, right? When thinking about water, water vapor seems to be the lightest. So it has the smallest density. Ice floats on water, so it seems like ice has a lower density than water. Therefore, I feel like the density increases in the order of gas, solid, liquid.
You're thinking logically, Oliver. However, the general relationship of the density of substances is that it increases in the order of gas, liquid, solid. Normal substances are heavier as solids, so if you put a solid into a liquid, it will sink. In fact, if you freeze salad oil in the freezer and put it in liquid salad oil, the ice made from oil will sink because it has a higher density than the liquid oil. This is a simple experiment, so you might be interested in trying it out.
When I get home, I'll try it out. But while most substances increase in density when they freeze, why does water's density decrease when it freezes?
That's because water forms a unique crystal structure. It's a pretty special substance. Water is such a common substance that we might not realize how special it is, but it has some pretty interesting properties.
I think you've mentioned something similar before. I remember you telling me that water has a much stronger surface tension than most substances due to its hydrogen bonds.
I'm glad you remember. Water has a lot of unique properties, or singularities, besides surface tension and the difference in density between its solid and liquid states. I'll paste the URL of a page that introduces the peculiarities of water in the summary section, so take a look if you're interested.
Understood.
Now, let's explain why water becomes lighter when it freezes. Normally, when a substance becomes a solid, the particles that make up the substance line up regularly, forming a crystalline structure. Things like glass, even when cooled and solidified, do not form a crystalline structure, but rather become a state of a liquid that has become immobile. Not all substances line up their contained particles regularly when they become solid. But for simplicity's sake in this explanation, let's proceed with the premise that normal substances form a crystalline structure when they become solid.
There's something I'm curious about, but it seems off topic, so I'll refrain from asking now.
When it forms a crystalline structure and particles line up in a regular pattern, normally, a large number of particles are densely packed into a small volume, which increases the density.
Yeah, I can intuitively understand that.
On the other hand, it's a little different when it comes to water. When water freezes into a solid, the molecules line up in a regular pattern just like normal substances. But in the case of water, it doesn't form a densely packed crystalline structure like other substances, but creates a structure with quite a lot of gaps. In other words, when water freezes, it turns into a crystal structure with a lot of empty space inside, a state of water molecules in the liquid state, where they are relatively freely positioned. The molecules end up being densely packed.
I see. With ordinary substances, particles become more densely packed when they are arranged in a regular pattern rather than being in random positions. In the case of water, the crystal structure has a large amount of empty space, so having particles in random positions results in higher density.
Exactly. Substances where the liquid state has a higher density than the solid state are really limited. There's hardly anything other than water and a substance called bismuth.
Even though there are so many types of substances in the world, The fact that there are only about two substances, water and another, that have a lower density in solid form than in liquid form, really makes water a unique substance.
Even just the substances that humans have identified, there are 200 million types in the world. Water really is a mysterious substance, and due to its property of having a lower density as ice than as water, ice can float on water.
I see. From what we've discussed so far, I understand that ice has a lower density than water, which is why it can float on water. But how does this relate to the fact that the ice water we filled to the brim didn't spill over even after all the ice melted?
For that, you need to understand the concept of buoyancy. Once you understand both the property of ice floating on water and the relationship with buoyancy, I think you'll be able to understand why it didn't spill over.
I wonder if I can fully understand it.
I'll try to explain it as simply as possible, and it's okay if you don't understand everything, so don't worry. What's your impression of buoyancy, Oliver?
Well, I have an image of it making things lighter when they're in water.
That's not entirely wrong. To add a little, buoyancy is a force that also works on things that are in substances other than water. Actually, it's working on us right now.
Hey, really? I don't feel it at all. Why do you think we don't notice buoyancy?
There are various reasons why we don't feel buoyancy in our daily lives, but one of them is because the buoyancy is too small. It's too small for us to notice, but buoyancy is definitely working on us now.
I'm suddenly interested in buoyancy. When was buoyancy discovered in the first place?
The existence of buoyancy was discovered by Archimedes, an ancient Greek scientist, around 200 BC. It seems Archimedes came up with the concept of buoyancy when he saw water overflowing from his bathtub as he got in. Whether it's true or not, when Archimedes realized the existence of buoyancy, he was so overjoyed that he ran out naked, and this anecdote has been passed down.
If you did something like that today, you'd be caught in an instant.
Buoyancy is common sense to us, but it wasn't known at that time, so he must have been very happy when he thought of it. The law of buoyancy is called Archimedes' principle because it was discovered by Archimedes. In a nutshell, Archimedes' principle states that when you put an object in a fluid, it means that the weight of a fluid with the same volume as the object acts as buoyancy.
What exactly is a fluid?
Simply put, a fluid refers to liquids and gases.
So does that mean buoyancy works even inside a gas?
Yes, that's correct. Earlier, when I said that buoyancy acts on us too, it means that we are receiving buoyancy from the air. One of the reasons we can't feel this buoyancy is because it's weak. The reason for the weakness is that the buoyancy that works on us only exerts a force equal to the weight of the volume of air in our bodies. The average volume of an adult body is about 71 L. In that case, the buoyancy that works on us is the weight of 71 L of air. That is only about 0. Therefore, the buoyancy we receive from the air has an effect of only about the same as reducing the body weight by less than 100. That's why we usually don't feel buoyancy. Well, another big factor is that we're always experiencing buoyancy, which makes it harder to feel.
Even if it's 100 Jack, buoyancy is definitely working on us. I didn't know that. I was just thinking, what is the principle that makes buoyancy work? I know that buoyancy exists, but I don't quite understand how it works.
Well, I'll explain it simply, prioritizing clarity. When you leave water as it is, no current is generated in the cup, right?
Yeah, of course. It would be scary if the water in the cup started swirling on its own.
If no current is generated, it means that the water in the cup is not moving. That is to say, it's as if no force is being applied.
Why can you say it's the same as if no force is being applied?
Well, when it comes to objects, if the total force applied to the object is not 0, it accelerates. For example, if you lightly push a floating balloon with your index finger, it moves a bit, right?
Indeed, that's true for balloons. But what about erasers on a desk? Even though only gravity is acting on them, they're not moving, are they?
No, in that case, a force called the normal force is acting on the eraser in addition to gravity.
What kind of force is a vertical reaction force?
The vertical reaction force is something you might feel most when you're at the bottom of a human pyramid in gymnastics. When you're at the bottom of the pyramid, your hands and knees hurt, don't they? That pain is felt because a vertical reaction force is applied from the ground to your hands and knees.
So that pain is caused by the vertical reaction force.
Yes, that's right. Let's go back to the topic. In the case of an eraser placed on a desk, the vertical reaction force is the force received from the desk. It's being applied in the exact opposite direction with the same magnitude as gravity. That is, because the same amount of force is applied in the opposite direction, gravity and force cancel each other out. The total force acting on the eraser becomes zero.
I see. I can understand that if it's not moving, the total force acting on it is zero.
I'm glad. And if the water inside the cup is not moving, the total force acting on the water in the cup is zero. Let's focus on a portion of the water in the cup. What forces do you think are acting on this portion of water?
I think gravity is acting on it.
Indeed, gravity is acting on it. But if it's only gravity, the total force acting on this portion wouldn't be zero. However, since this portion is not moving, the total force must be zero.
That's certainly true.
And the existence that explains this situation is buoyancy. Buoyancy adds the same amount of force to some of the water, equal to the weight of the water in the direction opposite to gravity. This is why the water inside the cup is not moving.
Oh, so that's the principle. So buoyancy can be explained by the condition that if the force on an object is not zero, it will move.
Yes, something like that. This buoyancy applies regardless of the type of object inside. It is understood that the same amount of force is applied if the volume is the same.
It means that the same amount of force acts regardless of the weight or shape as long as the volume is the same.
That's correct. Now that we've finished explaining about buoyancy, I'm going to explain why ice water filled to the brim in a cup doesn't spill even when it melts.
Finally, the main topic.
Yes. Oliver, how much do you think is the magnitude of the buoyant force acting on the ice?
Since it supports the weight of the ice, wouldn't it be the same as the gravity acting on the ice?
That's right. The fact that something is floating and stationary on the water surface means that the total force acting on it is zero. In other words, gravity and buoyancy are exerting forces of the same magnitude in opposite directions. Therefore, as Oliver says, the magnitude of the buoyancy becomes the same as the gravity acting on the ice. And according to Archimedes' principle, the magnitude of the buoyancy acting on the ice it becomes the weight of the water equivalent to the volume of the ice submerged in the water. From these two relationships, the magnitude of the buoyancy, the weight of the ice, and the magnitude of the buoyancy, the weight of the water equivalent to the volume of the ice submerged in the water. The relationship the weight of the ice, the weight of the water equivalent to the volume of the ice submerged in the water is derived.
Indeed, that's certainly true. But what is the relationship, which states that the weight of the ice is equal to the weight of the water displaced by the volume of the submerged ice, actually represent? I wonder what it's trying to convey.
Simply put, this relationship shows that when all the ice melts, it will fit within the volume of the water that the ice was submerged in. Even when the ice melts and becomes water, the weight doesn't change, right? So when the ice melts and turns into water, its weight remains the same as the weight of the ice before it melted. And from the earlier equation, the weight of the water after the ice has melted is the weight of the water equivalent to the volume of the ice originally submerged in the water becomes the same.
Indeed, even if it changes from the state of ice to the state of water, there should be no change in the number of molecules inside. The weight of the water after melting and the weight of the water equivalent to the volume of the part of the ice submerged in the water will be the same.
If you add the relationship that the density of the water does not change whether it was originally in the cup or came out of the ice, the conclusion is that the volume of the melted water is the same as the size of the part that was originally ice and submerged in water.
Since mass can be calculated as density times volume, if the mass and density are the same, the volume will certainly be the same.
And the fact that the volume of the water formed by melting is the same as the volume of the part of the ice submerged in the water means no matter how much the ice melts, the water level in the cup does not change and a full cup does not overflow.
I feel like I sort of understand.
Well, to put it simply, when ice melts, its volume just conveniently shrinks. Whether the ice melts or not, the water level does not change.
When the ice melts, only the part sticking out of the water shrinks. I now understand why the water doesn't overflow from the glass, even when the ice melts.
By the way, what about other substances? For instance, if I fill would the oil in the glass overflow, or would the volume decrease?
Except for substances like bismuth, which expands like water when it turns from solid to liquid. The result would be the oil overflowing from the glass. Firstly, as a premise, when ice is made from substances other than water or bismuth, the ice is heavier than the liquid, so it sinks. Then, when that ice melts, its volume is larger than when it was solid, so it overflows from the glass. In the case of ice, the ice was larger than the water, so it nicely shrunk when it melted. When other substances melt into liquid, they actually increase in volume, causing them to spill out of the cup.
I see, that makes sense. Thank you. I learned a lot.
You're welcome. By the way, a common misconception is that the rising sea levels due to global warming are caused by the melting of the Arctic ice. This mistake can also be explained with our discussion, because the Arctic ice is floating in the sea, just like the ice water in the cup didn't overflow. No matter how much the Arctic ice melts, the sea level will not rise.
Really? So the news about the rising sea levels, is that not true?
No sea level rise is actually happening. However, it's not because the ice in the Arctic is melting.
I wonder what's causing the sea level rise then.
There are mainly two reasons. The first reason is that the volume of seawater is expanding due to the rise in water temperature. It's not only when it changes from solid to liquid, but the volume of an object also changes with temperature. The second reason is that glaciers on land are melting. The ice floating in the sea, no matter how much it melts, is irrelevant to the rise of the sea level. However, when the ice on land melts, it's like adding water to the sea, causing the same effect.
I see, even if it's the same phenomenon of ice melting, the impact on sea level rise is completely different when it's ice floating in the sea like in the Arctic compared to when the ice on land melts.
Yes, that's right. Like this topic, if you know about science, your perspective on everyday news can change, and I think that makes you feel that science is interesting when such moments occur in everyday life.
That might be true indeed. I will try to study occasionally so that such moments can come.
I will support you as much as I can. So here's the summary for today. The reason why a full cup of ice water doesn't overflow when the ice melts is because the volume of the water perfectly contracts as it melts. Normally, the volume of a substance is larger in its liquid state than in its solid state. But water is a special substance, so its volume is larger in its solid state. When the volume increases, it means the density decreases, which is why ice floats in water. And when it floats, it means there are parts of the ice submerged in water and parts that aren't. When the ice melts, it becomes the same volume as the part that was submerged in water, so even if the ice melts, the water won't spill out of the cup. This principle can be explained by the balance of forces and Archimedes' principle.
I understand now.
That's all for today. Thank you for listening to me till the end. I plan to explain common questions like this, so please come to visit again if you like. So then, thank you for watching.
Thank you for watching.